Right, so welcome to, just checking. Welcome to Math 150, Section 2, Lecture 33, give or take. So what we're going to be doing today is we're going to be doing applications of some TaylorSeries. It's just having trouble recording just because of lights. Okay. The Section 1 video may be a little bit better to look at today because of lighting. Is that enough lighting for people? All right, so let's try that. All right, I will start the lecture, though, on a sad note. This is actually being serious. There is a reason why I have been doing so many things all semester to try to get you to be responsible, to learn time management, to get on track of just keeping track of things that are important. As you go further in life, you are not going to have people watching out for you. And so I was going to do two examples. There was a student at Yale who died in a chemistry lab at 2 a.m., did not put her hair up, got caught in a machine. I was going to talk about John Nash, who had just won one of the biggest awards in mathematics, $1 million, was flying back from Europe, wanted to get home fast, didn't put his seatbelt on in the car. He and his wife died, driver was fine. I will talk about a sad story my wife and I read in the newspaper this morning about a 15-month girl, Sophia Vero, who was accidentally left in her car by her mother, forgot to drop her off at daycare, died 9 hours later. You are not going to have people checking up on you and making sure you get things done. You've got to get in the habit of, if there's something that's important, if there's something that's valuable, you make sure you do it. The mother is now advocating a bag in the back campaign. Just leave something in the back that you need, your cell phone, something, your purse, your bag, so that when you try to go to your office, you have to go to the back seat and then you don't accidentally forget. This is why you watch the videos. This is why stuff like this, do the homework. You're not going to have people checking up on you, but you will lose opportunities if you don't do these things. So you really got to figure out what can you do to make sure you don't forget opportunities like this. All right. Happier note, TaylorSeries. So the idea of TaylorSeries is to take a small amount of information and do a terrific job approximating a function. So one way, if I wanted to approximate a function, is I could just evaluate it at a lot of different points and transmit that. But that would be a lot of information. The idea with TaylorSeries is you transmit a small amount of information and you do a great job of approximating the function. So if I have a function f of x, we'll say fn of x is the degree n Taylor approximation. I'll mostly do things about the point x equals 0. You can, of course, do things about the point x equals a as well. As a rough rule of thumb, the more terms you take, the better job you should be able to do. If people are not able to see, if this is too dark, I'll turn on the lights and we'll just watch the video from section 1. So are people able to see this, or should I turn on the lights?
Can you reread it?
Sure. Fn of x is the degree n Taylor approximation. Okay? So the more terms you take, the better job you should do. Then, of course, the question is, well, how do I measure error? Maybe the error is good at some points, worse at others. Do I do some kind of average error over some interval? Do I maybe concern myself more with the points closer to the expansion point and less as I go further and further out? So there are lots of different ways you can do it. Typically, we'll look at, h of x is f of x minus fn of x. So how much am I off at the point x? All right. And then there are lots of different ways. We're going to do a very prescribed method. So the more information we know, the better job we should do. So our first, the zeroth order Taylor series expansion is just f of 0. So the way you should look at it is, if the only information you know is the value of your function at time 0, then that's what you guess you are for all eternity. I don't know which way I'm moving, so I don't know if I'm more likely to get further or closer. If I do it at a general point, it would be f of a. The first order Taylor series is the tangent line, f of 0 plus f prime of 0 times x. Where I start, plus my instantaneous speed times elapsed time. And more generally, it would be f of a plus f prime of a x minus a. And x minus a would be the elapsed time. Okay, we can keep going, and now it's going to begin to get a little bit of interest. f2 of x will be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. And the 2 factorial is very interesting. And let's see why we have that. So if I take my second order Taylor series expansion and I take x equals 0, what do I get? So what would f2 of 0 be? So I'm putting in x equals 0. What would I get?
F of 0.
You just get f of 0. Good. If I'm trying to approximate my function, I at least agree at time 0. Let's calculate the derivative. Well, f of 0 is a constant, so its derivative is 0. What's the derivative of f prime of 0 times x? I'm sorry? Not f of 0. Close. What's the derivative of f prime of 0 times x? F prime of 0. F prime of 0 is just a constant. So f2 prime of x is just f prime of 0. And now I have f double prime of 0 over 2 factorial. Take the derivative of x squared. That's 2x. Okay. Now if I take x equals 0, what is f2 prime of 0? I'm sorry?
Is it just f2 prime of x?
No, I'm taking x equals 0. So in this equation here, I replace x with 0. So what would I get? I'm sorry?
You said you're replacing x.
I'm replacing x with 0. So f2 prime of x is f prime of 0 plus f double prime of 0 over 2 factorial times 2x. I now take x equals 0. So what would I get?
Is that just 0?
I'm sorry?
Is that just f prime of 0?
It's just f prime of 0. And this term would vanish. I can now calculate the second derivative of f2. Well, this is a constant, so its derivative is 0. So I get just f double prime of 0 over 2 factorial times 2 times 1, and the derivative of x is just 1. That 2 factorial is going to cancel this 2 factorial. What is f2 double prime of 0? What would that be? Yes?
F double prime of 0.
F double prime of 0. So what you're beginning to see is I'm choosing my polynomial very carefully. And that's why I have these factorials, so that when I take the derivatives, the derivative of the second order Taylor series expansion, its first derivative agrees with the first derivative of my function at 0. Its second derivative agrees with the second derivative of my function at 0. If I did the third order Taylor series, then it would agree up to the third derivative. Question?
Where do you get the second 2 factorial to cancel out the denominator?
Well, okay, so I start off with an x squared.
Yeah.
When I take one derivative, a 2 comes down.
Yeah.
And when I take my next derivative, I get a 1 comes down. 2 times 1 over 2 factorial. So that's just 2 factorial over 2 factorial. That's just 1.
Okay.
And so I'm left with just f double prime. If I had the term f triple prime of 0 over 3 factorial x cubed, the first derivative, a 3 would come down, and I would have an x squared. The next derivative, a 2 would come down, I would have it as an x. The third derivative, a 1 would come down, and now these would cancel. And this suggests that the following might be a really good thing to study. Is we should look at the Taylor series will be the sum, n goes from 0 to infinity, the nth derivative at 0 divided by n factorial times x to the n. So this will be the Taylor series expansion. Whenever you see an infinite series like this, what should be your first question? Does it converge? If it converges, then you can ask, what does it converge to? What would you like the Taylor series to converge to? So this is the Taylor series of f. What would you like the Taylor series of f to converge to? Yes? You'd like it to converge to f of x. If f is cosine, and I calculate the Taylor series of cosine, and I get an infinite sum that converges to sine of x, I'd be pissed. Right? I'm working to try to get cosine, and I got sine, I'd be upset. I want this to converge. So these are the two delicate questions. Does it converge? And if it converges, what does it converge to? The following is one of the worst functions in all of mathematics. G of x is e to the negative 1 over x squared if x is not 0, and 0 if x equals 0. It is because of functions like this that real analysis is hard. Complex analysis is easy because complex analysis does not allow functions like this to exist. This function is real differentiable, but it's not complex differentiable. If you remember, we talked about derivatives. Derivatives means a lot more in 2 dimensions. It's not enough just for the partials to exist. So this allows me to review some of the stuff we've been seeing all semester. It's not enough to have the limits exist along the x-axis and along the y-axis. It has to exist along no matter what strange path you take. In real analysis, if you're looking at just one variable, there's only 2 paths. And being differentiable does not imply that much. This function, it turns out to be differentiable. Now, if you want to calculate the derivative of this function, the derivative of this function is easy at every point but 1. What is the one point where it is hard to take the derivative of this function? 0. So we have to go back to the definition of the derivative. So g prime of 0 is the limit as h goes to 0 of e to the negative 1 over h squared minus 0 over h. Or the limit as h goes to 0, 1 over h e to the negative, e to the 1 over h squared. Okay? So we need to calculate that limit. I'm going to let k be 1 over h. So as h goes to 0, what does k go to? Yes, it goes to infinity. So this is the same as the limit as k goes to infinity. So 1 over h is k, so I get k over e to the k squared. What does k over e to the k squared go to? It goes to 0. We can do this by L'Hopital's rule. We can say, wait a minute, we know k over e to the k goes to 0. We've already done that. E to the k squared goes to infinity even faster. So this goes to 0. So it turns out the derivative of this function at 0 is 0. If you do a little bit more work, nice exercise, all of its derivatives are 0. Crap. If you look at the Taylor series for this function, every derivative is 0. So the Taylor series is a function that's identically 0. This function is not identically 0. This function is very small for long periods of time. If you were to plot the function, if you put in, for instance, x equals 1/10, e to the negative 1 over 1/10 squared, that's e to the negative 100. That's small. So this function is very small for long stretches. The series converges, but it does not converge to the function. So this shows you that the subject actually has some real meat to it. It is a difficult subject. We will ignore most of these issues in this class, but I want you to at least be aware of them. Okay? All right. So now let's turn to nicer functions. So we're going to start with the exponential function. So we've started with the exponential function, and we gave an infinite series expansion to it. All right, so let's take f of x is e to the x. So let's start calculating derivatives. What's f prime of x? All right, f double prime of x. All right, this is pretty easy. The nth derivative at x. E to the x. And then the nth derivative at 0 is 1. So the Taylor series of this function is actually pretty nice. All of the derivatives are 1. So I go into my formula and I just replace all of the fn's with 1, and I get, my Taylor series is the sum, n goes from 0 to infinity, of x to the n over n factorial. And fortunately, we already showed earlier, yesterday I think, that this sum converges for all values of x. And so this will give us our expansion. So this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc., etc. Okay. What I want to do now is I want to play a little fast and loose with mathematics. All right? So let's go back to the functions over here. I'm going to use a small amount of complex analysis. So you've seen this when you've tried to solve quadratic equations. I is, or I am, the square root of -1. So if I is the square root of -1, what would I squared be? -1. What would I cubed be? Negative what? So what would I cubed be? Yeah, negative root -1, or just negative I. Right? Because I squared is -1, I can write I cubed as I squared times I. What would I to the 4th be? And what would I to the 5th be? Square root of negative, or I. So when you look at the derivative, when you look at the powers, it's periodic with period 4. It goes, 1, I, negative I, 1. Did I do it right? Oh, here, I'm sorry. I, -1, negative I, 1. I, -1, negative I, 1. I, -1, negative I, 1. It just keeps repeating. This expansion is e to the x. Let's just formally look at e to the ix. Let's just put in an I and see what happens. We will then have a sum, and it goes from 0 to infinity, of ix to the n over n factorial. Okay. And there's going to be a change in behavior if we have even or odd. If n is even, I to the n is going to be either plus or minus 1. If n is odd, it's going to be plus or minus I. So I'm going to break this up into two parts. I'm going to write n as 2m. M goes from 0 to infinity. So we'll have ix to the 2m over 2m factorial. And then I'll have n equals 2m plus 1. M goes from 0 to infinity of ix to the 2m plus 1 over 2m plus 1 factorial. Okay? So the first piece, it's the sum, n goes from 0 to infinity. Then we have an I to the 2m. I to the 2m is I squared to the m. I squared is -1. So this is going to be -1 to the m, x to the 2m over 2m factorial. Now for this one, we have I to the 2m plus 1. So every term has an I. So I'm going to pull an I outside. We'll have a sum, n goes from 0 to infinity. We'll now have an I to the 2m. That'll be -1 to the m, x to the 2m plus 1 over 2m plus 1 factorial. Let's write this out. This is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, yada, 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 plus I, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, yada, yada, yada. Okay? That's what I get when I expand things out. It turns out this is the expansion for cosine of x, and this is the expansion for sine of x. And this leads to one of the most remarkable and useful formulas in all of mathematics. It connects the trig functions with the exponential functions. And so we get the following beautiful result. We get e to the ix is cosine x plus I sine x. So we used that earlier in the semester when we talked about proving all of the trig formulas in 5 minutes. Here's a rough derivation of where it comes from. If you want to prove the Taylor-series expansion for cosine, what's the derivative of cosine? Negative sine. What's the derivative of that? Negative cosine. What's the derivative of that? And what's the derivative of that? And you can see that when you take derivatives of cosine, it's going to be periodic with period 4. When you take x equals 0, cosine of 0 is 1, sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0, back to 1. So that the Taylor coefficients for cosine will be 1, 0, negative 1, 0, 1, 0, negative 1, 0. That's what we're getting right here. If you do sine, well, you just start over here and you still have the same periodicity. So it's always nice to see the connections between various things. So we now have expansions for sine and cosine. And later today, we'll see how accurately these model cosines and sines. Okay? Any questions on how we calculate these? Okay, so what I want to do now is I want to turn to logarithms. And we're going to spend a little bit of time calculating Taylor series expansions of logarithms. And the goal is to try to cut down as much as possible on our calculations. So what I'm going to do is I'm going to do a calculation and then show you how to get other results from it. And in fact, well, we're not going to really do too much of multivariable Taylor series until Monday. I'm going to show you a trick which for some reason is not often covered in books. Some books cover it, some books don't, that allow you to do multivariable Taylor series expansions just by knowing one variable Taylor series expansion if your function is nice. All right. So let's start off with the log of 1 minus x. So we have the log of 1 minus x. So that's our function. Okay, so we want to calculate its Taylor series expansion. If x is a small positive number, what do we get? Well, let's see. What is f of 0? What's the log of 1? 0. So if x is positive, do you expect the log of 1 minus x to be positive or negative? If you have the log of a number a little bit less than 1. So you should have, yes, it would be negative, right? And then if x is negative, you would have the log of a number a little bit larger than 1, and then it would be positive. So you should have some rough sense of what's going on. So when you look, you can see if the answers are reasonable. So I'm going to write f prime of x. I take the derivative of the log. I get 1 over 1 minus x. But then I have to take the derivative of 1 minus x, which is a negative 1. And I'm going to write this as negative 1 minus x to the negative 1. What's f double prime of x? So I have negative 1 minus x to the negative 2. And then I have another negative from this. How many negatives do I have? 3. It's still negative. So I get negative 1 minus x to the negative 2. Right? Let's calculate the third derivative. Negative, negative. I still have 3 negatives. It's always going to be negative. The 2 comes out, so it's now negative 2, 1 minus x to the negative 3. F4 derivatives would be negative 3 times 2, 1 minus x to the negative 4. Okay. I'm going to write this in a slightly more illuminating way. I'm going to write this as 1 times 1 minus x to the negative 2. And then I'll write this as 2 times 1 and 3 times 2 times 1. Why do you think I want to write it like that? Yeah, it's looking like factorials. And so when we try to figure out what we have, we need to evaluate these at x equals 0. And so let's see what we get. So f prime at 0 is just going to be negative 1. F double prime at 0 is going to be negative 1. Right? F triple prime of 0 is going to be negative 2 times 1. The fourth derivative at 0 is going to be negative 3 times 2 times 1. I can write this as negative 4 factorial divided by 4. And the reason I'm doing a 4 is because I have a fourth derivative. So I have 4 on my mind. For this one, I can write it as negative 3 factorial over 3. I can write this as negative 2 factorial over 2. I can write this as negative 1 factorial over 1. What do you think the nth derivative would be at 0? Yes?
Negative n minus 1 factorial. No.
It is negative n minus 1 factorial, but I want to write it in a special way.
Negative n factorial over n.
Negative n factorial divided by n. And the reason I want to write this is not only did I prepare the lecture in advance, but I've also just taught this class earlier today. Oh, it's been erased. But when it wasn't erased over here, we had the Taylor series formula. All right, so let me put that back on the board. But I know how the Taylor series is written. The Taylor series is the sum, n goes from 0 to infinity, of the nth derivative at 0 divided by n factorial times x to the n. I'm going to be dividing by an n factorial, so if I have my n factorial there, things are going to look very nice and cancel. Now, we know that f of 0 is 0, so I can start my sum at 1. And so this will be the sum, n goes from 1 to infinity, of negative n factorial divided by n factorial times x to the n. So I'm actually a little bit sad. We're happy when we look at the Taylor series formula because we've got this n factorial down below. That gives us great convergence. We know x to the n over n factorial converges for any choice of x. As long as the derivatives aren't growing too rapidly, we'll have convergence. Well, unfortunately, the derivatives are growing rapidly. And they're growing so rapidly that they kill most of the n factorial. And we're left with just negative, the sum n goes from 1 to infinity, of x to the n over n. 1 negative x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, etc. And so this is the Taylor series expansion of the log of 1 minus x. And what's nice is you can see if x is a small positive number, this will be negative. Great. So the question is, does this series converge or diverge? And does it depend on x as to whether or not it converges or diverges? Can somebody give me a reason why this might want to diverge? Can someone give me a reason why this might want to converge? So when you look at this, what might make you think diverge? Yes?
Exponential grows faster than
I'm sorry?
polynomial. Like the exponential function grows faster than.
So the exponential grows faster than the polynomial, but we no longer have exponentials. We just have polynomials in the numerator, and we have your 1, 2, 3, 4 integers in the denominator. So does either one of those give you a thought of convergence or divergence? The 1x squared x cubed, also the x squared x cubed, or the 1, 2, 3, 4? Not sure.
Well, if x is large, it doesn't tend to 0.
If x is large, it doesn't tend to 0.
So it diverges.
So it would diverge. In fact, what value of x would be enough?
1.
At 1, the terms will tend to 0. But if x equals 1, you have 1 plus a half plus a third plus a fourth. What is that? It's the harmonic. So at x equals 1, it will diverge. If x is greater than 1, it's going to diverge. We can actually do a comparison with the geometric series. If x is less than 1 in absolute value, we can compare this to a geometric series, and it will converge. So if the absolute value of x is less than 1, then x to the n over n is less than or equal to absolute value of x to the n. And now it will converge by comparison with a geometric series. Okay. So we've got some good results here. Now I want to make your life harder. And instead of doing the log of 1 minus x, I want to do the log of 1 plus x. I'll call that g of x. So does everyone agree we can go through and do the same calculation and get an answer? Yes? I'm going to show you a way to avoid having to do that calculation. So we want to calculate the expansion of the log of 1 plus x. We know if f of u is the log of 1 minus u, this is just negative sum n goes from 1 to infinity of u to the n over n. That's what we just showed. I want to calculate g of x is the log of 1 plus x. I am trying to write this in a very illuminating manner. What should we take for u?
Minus x.
Yeah, take u to be minus x. So if we take u to be minus x, we can just pull in the result for the log of 1 minus u, and we don't need to do any new work. And so now we get g of x is the log of 1 plus x. It's going to be negative the sum n goes from 1 to infinity of negative x to the n over n. So it's going to become the following. There'll be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And now the question is, does that series converge or diverge? Well, if x is greater than 1 in absolute value, we know it diverges. If x is less than 1 in absolute value, it will converge. What happens if x equals 1? If x equals negative 1, it's going to just be negative harmonic series. It's going to diverge. So the interesting thing is if x equals 1. Well, if x equals 1, what is the log of 1 plus 1? 2. So if we take x equals 1, we have the log of 2. And does that equal 1 minus 1 half plus a third minus a fourth? And the answer is yes. This is an expansion for the log of 2. And there's one last test which we haven't done. It's the alternating series test. So if you have a sequence of terms that alternate, if an alternates positive, negative, and the absolute value of an is greater than or equal to the absolute value of an plus 1, then the sum n goes from 0 to infinity of an converges. So this is a really nice result. So if you have a sequence of terms that alternate, what is essentially going on is you have so much cancellation that things will converge. So I'm going to do proof by example. Let's look at the alternating harmonic series. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. Okay? The series alternates, and each term is no larger than the previous. So if I stop at 1, and I look at what comes from this point onward, negative a half plus a third, is that positive or negative? Negative. Negative a fourth plus a fifth, positive or negative? Negative a sixth plus a seventh, positive or negative? I'm sorry? Negative. So if I stop at 1, everything from this point onward is negative. So I know the final sum is less than 1. What if I stop at 1 minus a half? What's a third minus a fourth? Positive. A fifth minus the sixth? Positive. So we know less than 1, and now we know greater than 1 minus a half. And so we just keep alternating like this. If we did 1 minus a half plus a third, it would be less than that. So it's less than 1, and it's less than 1 minus a half plus a third, and it's greater than 1 minus a half plus a third minus a fourth. This is a sequence of numbers that's going down. This is a sequence of numbers that's going up. and they're converging to a common value, and that common value is what it converges to. So this is the alternating series test. And so while the harmonic series diverges, if you just put in these minus signs, it converges, and it converges to a really important number, the log of 2. Okay. Any questions on what we've done so far? All right. So for the last part of the day, I want to do some Mathematica code and videos. So this part is almost surely not going to record well. So for those of you who are not here right now, you will just have to look at the Mathematica notebook. Okay. So Mathematica has a beautiful command called manipulate, which allows you to dynamically change certain values that you're looking at. Okay. Okay. So what I have done here is I've plotted cosine of x, and I have 3 parameters that I'm allowing myself to play with. X naught is my starting point, n is the number of degrees in my Taylor series approximation, and c is just some kind of scaling factor. Do I want to zoom in or zoom out? So for instance, if I want to zoom in, then I can zoom in a little bit, or I can zoom out a lot. Right, so this looks like a decent level of zoomation. Okay? This is the first order Taylor series expansion. Are you surprised that it's just a straight line? Well, it's the first order Taylor series expansion is the tangent line approximation. It's f of 0 plus f prime of 0 times x. Now I can change my expansion point. Rather than doing the point x equals 0, I can change, and here's another point. Now let's zoom in and see how good of a job it does. Okay. So the question is this doing a really good job of approximating? And for those watching at home, it's like 2 polar bears at the Antarctic right now. Is it missing by a lot over here? Remember the XKCD of the person who was breaking up with their significant other and provides the documentary evidence. Here's the scientific analysis of why we should break up. And the significant other looks and goes, I agree with you. And the original person says, I knew the evidence would be convincing. No. You didn't label your axes. I can do better than someone who doesn't label their axes. You can't just look at axes without knowing what's going on if you don't have any labels. This is going from 1 to 0.9995, 0.9985. This is probably 0.998. It's not really changing by that. It looks like it's changing by a lot, but it's not changing by that much. You really want to look at how much are you off by versus how much you've moved. I've moved 0.06, and my error is 0.002. My error is much smaller than how much I've moved. It's actually doing a pretty good job approximating. So you really want to get in the habit of looking at labels. So I'm going to zoom out a little bit, and let's move the point. Move the point. Okay. And now let me zoom in. That looks like a really good fit. The reason it's doing a good fit is it's showing up on the scale. I'm now at a point where the first derivative is not 0, so the tangent line is looking really good on this scale. All right, let's zoom back out. I'll go back to x naught. So I'm going to now go up to the second order Taylor series expansion. And I'll zoom in a little bit. So I'm now looking at 1 minus x squared over 2 factorial versus cosine. Good fit or bad fit? It's not too bad. I mean, if you look at it going all the way up to 1, the difference is not huge. And if I'm only up to a half, the difference is very small. So just using the degree 2 Taylor series expansion, I'm doing fairly well. What do you think would happen if I used a degree 3 Taylor series expansion? Do you think it would be better? Let's see. No change. Why was there no change when we did degree 3?
Is it 0 degree?
Because it's 0 degree 3. Remember, the odd coefficients vanish for the cosine. So when I go to degree 3, I'm not actually gaining anything. My approximation function doesn't change. Let's go to degree 4. So we'll go up to the x to the 4th term. And if I zoom out a little bit, not surprisingly, it's getting worse as I go further out. Let's go up to degree 6, degree 8, degree 10. So I'll zoom out a little bit. Degree 12. So with degree 12, we almost have a complete period of cosine with almost 0 error. So in terms of transmitting information, I can transmit the cosine function by just sending essentially 12 numbers. And rather than getting a better approximation by evaluating my function at more and more points, which is expensive, all I do is I transmit more and more Taylor coefficients. Let's bump it up to 31 coefficients. And so with 31 coefficients, I'm basically getting an almost perfect fit well past 10. I'm getting several cycles of cosine. So I hope this shows you the power of Taylor series and why we care about this. It allows you to transmit massive amounts of information very cheaply. Okay, so we have a few minutes left. And so what we'll do for the last bit of class is I will just give you a quick introduction to multivariable Taylor series expansions without saying what a multivariable Taylor series expansion is. All right. We're going to have to worry about taking partials with respect to all the different variables and figuring out how the formula generalizes. Let's say f of xy is cosine xy. And I want to calculate the multivariable Taylor series expansion of this. Well, I know the cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial, etc., etc., etc. So what should I take u to be?
XY.
Yeah, take u to be xy. Then you get the cosine of xy is 1 minus xy over 2 factorial, this is x squared y squared because I have to square it, plus x to the 4th, y to the 4th over 4 factorial. And there you go. I can now approximate cosine xy. If I wanted a degree 2 Taylor series expansion, I would take terms only up to degree 2. What's the degree of the term x squared y squared? Degree 4. X to the 4th, y to the 4th, what would its degree be? If I gave you x squared y to the 4th, what would that be? It would be 6. You just sum the exponents. So if I want degree 2, it would just be 1. If I want degree 3, it would just be 1. If I want degree 4, it would be up to here. So would degree 5, 6, and 7. Degree 8 would be up to there. So this is a really nice trick to calculate Taylor series expansions of several variables if you happen to know the Taylor series expansion of one variable. You just say, let's take u to be xy. All right, question? Yes?
Just a quick question. So like the second order, third order are both 1.
They're both 1.
And then
And the 4th order is 1 minus x squared y squared over 2 factorial. And then the 5th, 6th, and 7th are also up to here.
yeah.
And you basically, the degree n, you only take terms whose degree is n or less. Okay, so what I want to do now is I want to do a slightly harder second order, Taylor series expansion in 2 variables. It's going to be the same general idea. So instead of cosine of xy, let's look now at the cosine of x plus y squared. All right? So the first thing is, what function does this look like? So I want a function of u. What function does this look like? So I need to have a function of just one variable that I understand.
Cosine of u.
It looks like cosine of u. And the expansion of cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial. What should I take u to be?
X plus y squared.
x plus y squared. And now I play the game as before. So the cosine of x plus y squared should be 1 minus x plus y squared over 2 factorial plus x plus y squared to the 4th over 4 factorial. And now things get a little bit more painful. Because before, all the terms in a given slot had the same degree. When I expand to x plus y squared, I get x squared plus 2xy squared plus y to the 4th over 2. What's the degree of x squared? Degree of xy squared. And degree of y to the 4th. So the problem is they all have different degrees. For the next one, I'm going to get x to the 4th plus 4x cubed y squared plus 6x squared y to the 4th plus 4x y to the 6th plus y to the 8th over 4 factorial. So as you go further and further down for this, it's becoming more and more of a nightmare. Yes?
That up there should be like x plus y squared, right?
Yes, thank you.
Okay.
Yes. So this term has terms of degree 2, 3, and 4. This term has terms of degree 4, 5, 6, 7, and 8. What will the next one have terms of degrees from what to what? We'll have x plus y squared to the 5th. To the 6th. It'll be degree 6 to 12. The x to the 6th will be the lowest. The y squared to the 6th will be the largest. But the important thing to note is everything from here onward will have at least degree 6. The next term will be at least degree 8. The next term will be degree at least 10. So if I only want, say, a Taylor series of degree 8, well, I would have to worry about this, because that would give me an x to the 6th. And it would also give me a x to the 5th y squared. But if I only want Taylor series of degree 5, I don't have to worry about this. Because all the terms from this will be degree 6 or higher. And the next one will be degree 8 and higher. So if I only want a Taylor series of degree 5, which terms survive? Lives, 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 gone. Right? Because this is now degree 6. So if I wanted degree 5, I would stop at 4x cubed y squared over 4 factorial. If I wanted degree 4, I would stop at x to the 4th. I would include all of this stuff, x to the 4th over 4 factorial, and then nothing else. If I wanted degree 3, I wouldn't include anything from here, and I would stop at xy squared, and I wouldn't include the y to the 4th. Yes?
How can you break up that polynomial? If you wanted just degree 4, you can just break it up at x.
Well, what I'm saying is, for each of these, which terms are degree 4 or higher?
Right.
X to the 4th is degree 4. X cubed y squared is degree 5. What you typically think about is when you're expanding, x and y are going to be small numbers. They're movements from your expansion point. So if x and y are small, something of degree 5 is going to be smaller than something of degree 4. And so when we're doing the expansion, it's like the tangent line. It's not perfect, but the next correction is going to be of size x squared. If x is 1 over 100, x squared is 1 over 10,000. So I would just chop off however many terms. It's a little bit painful when you have something like this because it's more work. Almost surely that will be on the exam. I don't know. I haven't looked at the exam in months. All right. Any other questions? All right.